What is going on, everybody, and welcome to part 3 of our Deep Learning with Neural Networks, TensorFlow, and Python tutorial. In this tutorial, we're going to be going down the rabbit hole and beginning to build our first deep neural network. So to start, I'm just going to go ahead and copy this. We'll rename it to DeepNet, and we will edit with Sublime. Minimize this, make this big, and we'll just delete all of this. Okay, so before we get started, we're going to be using the MNIST dataset for a few reasons. The main reason we're going to do this is because gathering data and just kind of preparing it to be used in machine learning is a pretty long and tedious process. So we will eventually do something like that, but if you are familiar with maybe the investing with the support vector machine series I did, probably 80% of that tutorial was spent just getting the data in the right format, right? So the MNIST dataset, it's really nice because the data is already in the right format and stuff like that. And so we can very easily work with this dataset and first focus on the neural network itself, modeling the neural network, training the neural network, working with TensorFlow. We can focus on that first, and then we can worry about, okay, from here, how do we do our own project and stuff like that? So, so that's what we're going to be doing. We're going to be working with the MNIST set to begin. Now, the MNIST dataset is a set of 60,000 training examples of handwritten digits, so anything from 0 to a 9. And they are all 28 by 28 pixels, so 784 total pixels. And then you have 10,000 testing examples. So we train against those 60,000, and then we test against those 10,000 samples. And those 10,000 samples are unique, right? They're not the same as the stuff that we trained on. So the objective is to take these MNIST 28 by 28 images of handwritten characters. They're just black and white thresholded images. Take those and somehow pass that through a neural network to the point where the neural network can somehow model what's going on here and output, when it comes time to predict, output the correct number of whatever handwritten digit we pass through. That's in a 28 by 28 at least. So that's the objective. Now, with this basic neural network, the way that we're doing that are basically each of our features is just a pixel. It's just the pixel value, right? Is this pixel on, basically, well, it's not a pixel value, but it's basically a 0 or 1, right? Is there something there in that pixel, or is it just white space, right? Is it part of the number, or is it white space? And that's it. Those are our features. And from that, somehow, we're hoping, our neural network is going to somehow model this relationship and be able to do things like figure out whether it's a 1 or a 7 or a 4 or a 9 and so on. Okay? So first, before we start writing code, I'd like to kind of condense a little bit what we're going to be doing. So I'll just kind of write it on here just really quickly. Just as a quick recap. So first of all, we have our input data. And we send the input data to the, let's say, hidden layer 1, okay? On the way, we send the input data, we weight it, and then it goes to hidden layer 1. And that's with unique weights. And then from hidden layer 1, we're going to run that through some sort of activation function, okay? And then we take that and send it on, along with weights, to hidden layer 2. I'll just say hidden L2 for now. Oh, it already, nice. Okay, whatever. Let's do this. Okay. And we repeat this process up until, again, hidden layer 2 has an activation function, which then will send off with weights to, let's say, the output layer. Okay, something like that. Now, I guess I'll leave it that simple for now. So that's what happens. And in a typical neural network, we pass data straight through, okay? That passing of data that goes straight through to the very end, that's feed forward. So this is a feed forward neural network. So we pass that data straight through, and then at the end of it, we compare the output to intended output. Okay, how close is it? And the way that we compare that is with a cost or loss function. And I'm just going to say or here, just in case you saw that and it was like cost divided by loss. No. Anyway, compare the intended output. That's a cost/loss function. I'm just going to say cost function because I don't want to say or either. Anyway, so you compare the output to the intended output with the cost function, and then finally, and like an example of a cost function, I don't know, cross entropy. Okay, this is how close to, or how wrong are we, or how close to what our intended target are we, or how not close. Then that's your cost function, and then we're going to use an optimization function or an optimizer. We'll call it optimizer, and that is going to attempt to minimize that cost. Okay, and the example here that we're going to use is we're going to use the atom optimizer, but there's also stochastic gradient descent, attograd or atagrad, and like even in TensorFlow there's like 8 or something that you could use. So there's a lot of options there. And what that does is it goes backwards and manipulates the weights. That backwards motion and the manipulation of weights, that's your back propagation. Okay? And then feed forward plus back prop equals an epoch. Okay? That's one like cycle of feed forward and back prop. That's an epoch. And you're going to do that maybe 10 times, 15 times, 20 times. And after so long, hopefully each time you cycle through, you're lowering the cost function. And eventually you'll get to a point like initially you'll start like the cost will be really high. And let's see if I can do this right. If it was over here. So the cost is like really high. And then as time goes on, it kind of drops down and then it kind of like levels out. And sometimes it'll kind of wiggle a little bit and you might go backwards. Your cost might actually go up or something. And that, at that point, you've hit your diminishing returns and it's no good and you're just not really making any more progress. So we'll probably do like 10 or something epochs. But anyway, that is basically what we're doing. Hopefully that was a quick but useful summary, just in case some of you were a little confused about what goes on. Now, I'm actually going to get rid of this because without my talking along with writing this out, this is probably really confusing looking. So I'm going to get rid of it. So now that we have that, let's prepare for liftoff. So we import TensorFlow STF. There's really nothing fancy going on there. And then from, whoops, I'm not even in my window here. From TensorFlow.examples.tutorials.MNIST, we're going to import input data. And then we're going to say, I don't want that on that line. We're going to say MNIST equals input data.read data sets. And then we'll have it in temp and data. And then we're going to say one hot equals true. Great. So the only thing to note here is the one hot parameter. Okay, this term comes from electronics and circuit boards stuff where like one component will be hot and that like dictates something. So and then the rest are off. Like one hot literally means one is on and the rest are off. Okay, and it's like literally like if it's physically has electricity running through it, it's probably hot. So an example here is, well, first of all, why are we using this? One is it can be useful for multi-class classification. So the output from our neural network is going to have, say, like 10 output nodes or something. So for example, we have, this is multi-class, we've got 10 classes, right? So we have 10 classes, and they are either a 0 to a 9. They're handwritten digits, 0 to a 9. So normally you might say a 0, we want the network, and in fact, let me just make a comment out of this, just in case I leave it. You might say you want 0, you want the output to be a 0. A 1, you want the output to be a 1. A 2, and a 2, and so on. Well, what one hot's going to do instead is it's going to say 0 actually outputs to be a this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so a 0 is actually a 1, 0, 0, 0, 0, 0. Okay, so I'll copy this just for a couple examples. So 1, 2, and a 3. and it'll actually be like a 1 would be a 0, 1, 0, 0, 0. And then a 2 would be a 0, 0, 1, 0, 0, 0, 0. And a 3 would be the following, and so on. So under a one hot situation, it's just literally one pixel or one element is on or hot, and the rest are cold or off. All right, so we have our data. And now what we're going to do is actually start kind of defining our model. So we're going to start by saying n nodes for the hidden layer 1, and we're going to say is 500. And we're just going to say this, and we're going to have 3 hidden layers. So this is a deep neural network. So 2 and 3. Okay, so 500 for each. Now, these don't have to be identical. You could have this one be 500, this one be 1500, and this one be 15. Okay, 500, 500, 500 will be good enough to start with, but feel free to tweak that depending on what you're doing, how many layers you have, and what kind of model what kind of thing you're trying to model. This can be totally different, but this will be fine, hopefully. And then we're going to have number of classes equals 10. I would imagine through MNIST you could probably derive this value, but we'll just do this. And then, like I was saying before, MNIST is a small enough data set that I would wager most of you could probably load all of MNIST. Well, they are 28 by 28, but most of you could probably load the MNIST data set into your memory, or so I think. But that doesn't really prepare you for the future, and the reality is that you're going to have like a data set that might have millions and millions of samples, and might, like for example with Common Crawl, that's got petabytes of data. Well, you probably don't have petabytes of RAM. So unless you're watching this tutorial in like, I don't know, 50 years or something, maybe even less, who knows. But anyways, you probably don't have petabytes of RAM. I'm still trying to think about how many years will probably be until we have petabytes of RAM. Probably not that long. Anyway, but regardless, we're going to say the batch size, back on topic, is 100, okay? And so what this is going to do is it's going to go through batches of 100 of features and feed them through our network at a time and manipulate the weights, and then do another batch and manipulate the weights a little bit. So it's just by batches of 100 images. We could do 1,000 images or something else, but 100 should be fine enough. So now what we're going to do is define a couple placeholding variables. So x is going to be tf.placeholder, and then it's going to be a float. And then we're going to define y as the same thing. One thing I will note is it's not necessary, but you can define these. So for example, x, this is your input data. Okay, so the input data will have a very specific shape. It's just going to be 784 pixels wide. Okay, and a matrix is height by width. So the height, let's say, of the x data set, what would the height be? Well, you're not going to have any height really, so that would be none. And then the width is 28 by 28, because what we're going to do is we're just going to flatten or squash, I think is the proper term, or flatten. I'm not sure which one's the proper one. Someone can comment below and tell me which one's the proper term in this case. Maybe they're both synonymous. I don't know. Anyway, and then also this needs to be a quote. This is a different, or a comma. That's a different parameter. Anyway, the second parameter here can be a shape. So none, and then it's a 28 by 28, which we're going to just flatten out or squash out to be 784 pixels, or actually just 784 values. So even though it's coming in as a picture that's a unique, 28 by 28. So in theory, you might be thinking, oh, the matrix should be 28 by 28. It's really not necessary. As long as they maintain the exact same position, they can just be a string of values. It doesn't actually have to maintain the initial shape of the array. So anyway, you can do this, and you don't have to have these values here, but what happens is if you attempt to feed through something that is not of this shape into this x value, TensorFlow will throw an error. If you don't have it there, and something not of that shape gets attempted to be placed into X, TensorFlow won't throw an error. So sometimes it can be useful to leave something in there, because a lot of this stuff is happening behind the scenes and you're absolutely not privy to what's going on. So when things don't go the way you hoped, this can be kind of helpful. But anyway, just keep that in mind. Sometimes it's useful, sometimes not. So, so we've got our starting values, right? The X is our data, the Y is the label of that data, and basically what will happen is this is just a placeholder, and at no point are you actually going to have any code. Well, you kind of will write the code that handles X and Y, but because X and Y is just a placeholder at any given time for some data to be shoved through the network. But I guess we'll wait till we get to the weights. But that's where I just don't want to forget, because the weights is a perfect example where like we have no code that suggests that, oh, let's modify weights here. TensorFlow just does it. So anyway, we'll get there. So now what we're going to go ahead and do is we're kind of done defining our constants and our variables. So now we're going to define our neural network model. And the neural network model just needs some data to be passed through it, right? This is your raw input data. I'd use the word input there, but that would violate some Python. So anyways, here we're going to start just with some dictionaries. So we're going to say hidden one layer, and hidden one layer is going to have two values in the dictionary. So you're going to have weights, and you're going to have weights equal to, and this is going to be kind of long, but anyway, tf.variable, and then hopefully this won't run us off the screen. tf.random normal, and then of a shape. So it's a TensorFlow variable, the weights, right? The weights here are a TensorFlow variable, and then that variable is a TensorFlow random normal. And what we're going to do is we're going to specify the shape of that normal. Okay, so the weights, what would this be like? So for the weights, for example, we're going to have, it'll be 784 by the number of your nodes in the hidden layer 1, HL1. That's your weights. Those are all of your weights. So this is just going to create a tensor or an array of your data using a bunch of random numbers, and that's just those are your weights now. So now you've got your weights in one giant tensor, basically. And that tensor is a TensorFlow variable, of course, and it was generated with tf.randomNormal. But obviously, soon enough, we're going to start modifying that, but we have to start with something, so we just start with something random. Next, we are going... Ooh, I really wish it didn't do this. Idle doesn't do this. This is why idle is the best. Hopefully this won't throw us for an error later on. Like normally if you hit it, unless I did close it off, right? Yeah. Hopefully this will be kosher. Anyway, weights, and then we're gonna have biases, and the biases similar will be tf.variable. The tf variable will be a tf.random. Random normal. And then this one, the biases, recall, let me write it out first. Number nodes, hidden layer 1. Okay, so in this case, do you need it to be any sort of shaped tensor? Not really. The bias is something that's added at the very end. And actually, just realizing, everybody's probably like, what the F are biases? What the hell? Okay, so biases are something that's added in after the weights. Okay, so as the weights come through, so you've got your input data, and then you've got weights. And so the weight is the input data is multiplied by the weight. And then we were saying before that the weight comes through and is just all those inputs are summed together after their weights are multiplied by the input data. Well, what a bias does is adds to that. So you've got basically the formula that's going to happen is you're going to have input data, we'll call it input data, times your weights plus bias. And it'll be like this. Okay? So why do we even have a bias, right? Because we haven't talked about a bias at all up to this point. Now, we're going to be using this activation function that's rectified linear, and so the biggest benefit for a bias in this case is if all of the input data is a 0, that would be 0 times weights, which would be 0, of course. So no neuron would ever fire. Okay. And that's not really ideal in every scenario. And so you have a bias, which is yet another parameter that we will have to like deal with. But a bias comes in and just adds a value to that. So at least some neurons could still fire even if all inputs were a 0. So we add biases in there, and that's that. It also can make your network overall a little bit more dynamic. But mostly it's for if all input data was 0. This guy just throwing in biases. See, why is it acting like this? Why can I not... Like, did I not close this off correctly? Like, I feel like I did a good job closing that off. I feel like I'm going to get a syntax error or something. Let me, I'm just curious if I'm going to get a syntax error. I don't want to keep using this method here. Let's open up a terminal really quick. cd/desktop. So I am getting a thing. Did I not close off? Well, at least, yeah, in this case, I didn't close off the variable thing. So that's why it was probably giving me such a hard time. Did I close it off on this one? I did. It's just not this one. Okay, now what happens? Beautiful. So now what if I tab this over? Sure. Oh, that's still pretty unfortunate. Come on, Sublime. Okay, but it still looks like it's going to accept my code. Oh, pulling out the data. Everybody chill. All right, so cool. So we've got our hidden one layer. Okay, so now we're going to take this and we are just going to paste. Oh, gosh, it's killing me. Let's see if we can do this actually. So 1, and then we want... Really, we're going to do this... So hidden layer 1, 2, 3, and then we have the output layer. That's a lot of copy and paste. I encourage somebody to come up with some sort of dynamic for loop or something to iterate through a variable number of hidden layers. That would be interesting. Of course, you'd still have to have, you'd probably have to set like the max number of nodes, but it is possible, probably. Because imagine if you wanted to have like 100 layers. That wouldn't be very good, probably, at least for this problem. But anyway, I digress. So this would be 2, this will be 3, and then this is our output layer. Okay? So what is going to change? So one thing that can change, and one thing to note, is that these can change, right? One layer could have 500 nodes, that is 1,500 nodes. So those things can change. That's why we have unique values here, because you could change them. In this case, we've got them all as 500, but they can be variable. So generally what's going to happen is your weights, like in this case, the weights here wouldn't be necessarily 784. That's not necessarily the input. The input will be the number of nodes in the hidden layer 1, right? Multiplied by the number of nodes in the hidden layer 2. Okay? And then we'll take this, paste this in. This would be hidden layer 2, hidden layer 3. And in fact, this will, and then down here, right, the biases, this would be for the number of nodes in hidden layer 1. This would be the number of nodes hidden layer 2, hidden layer 3. And then in this case, in the output layer, we just explained what one hot, I got rid of it, but we explained what one hot was, right? What is the output of output layer 2, right? How many biases are we going to need in this case? Good answer. It's going to be, what is happening here? God, this is why I don't like fancy IDs. Anyways, the right answer is going to be the number of classes, right? However many classes we have, because that's the one hot, right? 0, 1, 0, 0, 0, 0, and so on. So that is going to be how many biases we need in the output layer. Now I kind of zoom through this. Let's see. Down here, this would be, we should have finished this. So this would be 3 by the number of classes. Cool. All right. So we've got that all defined. Okay, so hopefully everyone's clear on what weights and biases are. I know I just kind of threw the biases at you. I didn't want to throw that at you initially because the model, I think, makes more sense just with the weights part. But I meant to talk about biases before we got to the code of actually writing the bias. So I'm sorry, but hopefully that's easy enough. If you have questions, feel free to leave them below. So now all we have done at this point is, of course, just create variables basically for our layers. We haven't actually modeled anything. So remember the model, let's see if I got that. I do, well, at least this. Yeah, so this is the actual model. I'm going to cut that and I'll just paste it down here. That's the model that we have for each layer. Okay, so to start, let's say layer 1 is equal to tf.add, and then that would be tf.matmul for matrix multiplication. And we're going to multiply what in layer 1? Well, the input data, right? So data. And data, remember, data is coming from this variable here, data. So we multiply the data by the weights, right? And that would be hidden. This is kind of nice. Although I don't know how to get down. Probably the arrow keys. Hidden one layer. And then weights. Okay. Right? Weights. And then outside of those parentheses now. Don't make that mistake. Plus hidden one layer biases. Okay, so one mistake that I made before and could easily make as we go through is instead of having the closing parentheses there, I had it here. So instead it was tf.add together the matrix multiplication of data and hidden layer 1 weights plus biases. So it was like the weights plus the bias times the data, right? And basically adding nothing. So, but it still gives you that value. Like if you do tf.add like 5, the output would be 5. I think. Anyway, because everything ran, there was no error. It's just my accuracy was in the dirt, and I had to like figure out what the hell was going on. So, so make sure you don't make that mistake. So let's fix that. So again, input data times weights plus the biases, right? And as if you recall the little pretty picture I drew, right? You had the input data times the weights, and it went into that sum box, right? So this is your sum box. So then this information eventually, after we pass it through, like this is just layer 1, right? We haven't gone very far. So then it goes through, though, an activation function, right? And that's whether or not the neuron fired. Well, the threshold function would have been whether or not it fired. The activation function is this nice, beautiful sigmoid function, so it's not as on or off or all or none as a step function would have been. But anyways, continuing layer 1, this is just tf.nn.relu, which is rectified linear. That's your activation function, which is not synonymous, but it does the same thing as stochastic gradient descent. And I'm blank. Oh, no, it doesn't do everything. Sorry, it does not. I knew that sounded wrong. Okay, stochastic gradient descent, that's your optimizer. Sorry. Rectified linear is like your threshold function. And we just apply this to layer 1. Okay, so it takes whatever this value is and then passes it through that activation function. Whenever you've done that, you're going to bebop on to layer 2. Layer 2 is tf.add, and in fact, we're going to take this, copy, paste. Again, this is why a for loop would be great, but I cannot think of a really great way to like somehow just dynamically set the layers. Someone really wants to try though. And I also it would have to like work with TensorFlow, but there's got to be a good way. But even in like the TensorFlow docs and all the examples I've ever read, nobody seems to have that one figured out. But I know there's some Pythonista out there who's gonna get that fixed for people. Anyway, so for layer 2, what's coming through to layer 2? What is the input data? Is it data? No, it's the whatever that activation function returns for layer 1. Okay, so we take layer 1, that goes through. Are we using layer 1's weights? No, we're using layer 2's weights. And then same thing on the biases. Whose are we using? 2. And then while we're at it, let's just make that 3. and then this will be 3. And what's the information coming through to layer 3? Well, for layer 3, you have layer 2 data. Layer 2 data. And then, make sure this was all good before we... Okay, yeah, we didn't do this. Okay, so this needs to be layer 2. Whew. There's so many places to go wrong. Again, that's why a for loop would just be superb. I wouldn't have such messy code. Okay, so then what happens? After these 3 hidden layers, what happens is that you got your output layer. Paste. Okay. Output layer basically does the same thing. The only difference is the output layer doesn't go through a, the output layer is a little different. Sorry. It's not basically the same thing. Because first of all, you're not going through summation, and you're not going to run through the activation function. But you are going to matrix multiply. So this would be layer 3. Would it be hidden 3 layer? No, it's going to be the output layer. Weights and the output layer bias. And again, you could screw up with these parentheses, but since we've been copying and pasting, we did fine, hopefully. And then at the end of the day, we return the output. Boom. Whew. Okay, so at this point, we now have modeled a neural network. And at this point, we are basically done with the computation graph, okay, and setting up all the basics of the computation graph, and we are almost ready to launch into the session and actually train this thing and see how we did. There's like a couple variables that we're going to define right before we actually start the session, but they make more sense to define outside of this function, which is just our neural network model. But at this point, we've actually coded the model. Like, the model's done. Now all we have to do is explain to TensorFlow what to do with this model and what to do in the session. So anyways, if you have questions, comments, concerns, or you come up with a for loop that's going to accurately handle for this copy and paste here, this nonsense here, sort of, I still don't know how you're going to handle for those if you can make them dynamic, but I'd still like to see the for loop even if every layer is 500 nodes. But this copy and paste BS and then all this, at least this BS, all right, I can understand if the output layer is unique, but even then the output layer would just be like an addition at the end of the for loop or something. Anyway, got to come up with that. Anyways, questions, comments, concerns, leave them below. Otherwise, till next time.